Morning, Chris. How are you doing today?
Good, how are you doing?
Good. All right, so let's see if we can get started here. Let's see. I want to change. All right, so welcome to today's activity. What we're going to do is, as a first for me, trying to do the Exploring Pendulums lab. So this is a lab that I would normally do at the beginning of every unit looking at simple harmonic motion. We would do this kind of in isolation without a whole lot of information to go from at the beginning and kind of see how you do. I'm going to truncate a little of that because I'm going to be doing it myself for you and hopefully you can follow along. But the first thing I'm going to do is I'm going to share my screen with you of the pre-lab stuff. And hopefully you've had a chance to look at the pre-lab stuff. From the pre-lab stuff, you should be able to see a pendulum. And hopefully we know what a pendulum is. A pendulum is anything that has a fixed axis point, and you have some sort of mass, sometimes called a bob or a plumb bob, that hangs off of the end of that string, and it is set to oscillate, which means that you let it go from a high position, it goes to a low position, and then goes up to another high position and repeat. So other examples of this might be the Newton's cradle that I have at school, the little series of stainless steel balls that are connected to strings that you can have one hit and it makes the one at the other end bounce up, stuff like that. So that's kind of functions as a pendulum. Examples you might see of this in the real world, if you've ever seen a grandfather clock, they usually have a mass inside of them that is used to help them run. All right, so what you should see now is that pre-lab diagram of a pendulum. So there's an axis point in the center, and it shows the plumb bob at 3 locations. One of those locations is at the top left, one of them is at the center at the bottom, and then one of them is at the top right. And there's a little dashed line indicating the direction of its movement. It would go back and forth, back and forth. We are to label for our pre-lab each of these characteristics up here, maximum and minimum speeds. So I'm going to see if I can get some input from you guys, and if not, you'll have to talk to do this because I can't see the chat currently. Where would the maximum speed be in this pendulum? Just think about it. If it's oscillating back and forth, where is it going to be going the fastest? Any thoughts?
Maybe through the middle.
In the middle, because at the top, at each side, it comes to a stop and then reverses direction. And then when it's at the middle, it's going at its fastest, and then it continues on up till it slows down and then reverses and goes back the other direction. So its maximum speed, I'm just going to say max V, is going to be at the center position. See if I can fit all this stuff in here. And that tells us that minimum V is going to be at the top 2 positions. All right, so once we get that, hopefully the rest of these will kind of fall into place a little bit easier. We could analyze these with linear physics. We could say, oh, okay, well, I know that this thing is stationary here at a moment, and then it starts dropping. We know that it's got 2 directions of motion, X direction towards the center and Y direction down. Gravity is causing it to accelerate downward. There's nothing causing it to accelerate inward, or is there? Well, let's see if we can analyze this in other ways. We could do this rotationally. We could say, oh, hey, here's an axis of rotation at the center where the pendulum is connected. and it's making or describing part of a circle. So we could start looking at it in terms of some rotational quantities. All right, so next, maximum and minimum acceleration. Where does this thing experience the maximum acceleration?
At either end.
At either end, yeah, because when it's up here, what's causing it to accelerate when it's at the end?
The force pointing back towards the middle.
Okay, and that's something that we would call a restoring force. A restoring force is what we see in any kind of simple harmonic oscillator. There's something that's trying to push it back towards the center, restoring it to its center. So maximum acceleration, max A, would be out here. And same side on the other side, max A would also be at the end on the other side, which means at the center, it has minimum acceleration. Gravity is causing it to accelerate downward, 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 downward. And when it hits this point at the bottom, gravity can't pull it any further. The string is preventing it from going any further. So what happens is it starts going up because it still has some velocity, or its max velocity at this point, and it starts slowing down. It's slowing down because gravity is causing it to slow down. And it gets more and more effective gravity. Remember, in rotational systems, the maximum torque is when the force is perpendicular to the axis of rotation. So in this case, this is our axis of rotation. The farther up it goes, the more right angle the force of gravity is going to be affecting it. When it's down here at the bottom, the force of gravity is directly in line with the axis of rotation. There is no acceleration. If it could go up to a 90-degree angle from the bottom position to the side, exactly to the side, then it would have a complete 90-degree angle for the force of gravity. It would have maximum acceleration. So the endpoints are max acceleration. The middle point is minimum. Well, this next one's easy, maximum minimum force. What does it take to have an acceleration? Force. So if we've got max acceleration, that tells us that we're going to have max force up here. And max force always sounds like a superhero team. Max force. Max force. We're going to have max force up here at either end position. And then in here in the middle, clearly where there is no or minimal acceleration, we will have minimal force acting at the middle position. Next, maximum kinetic energies, minimum kinetic energies. What does it take for something to have kinetic energy?
Takes velocity.
Kinetic energy. What is it? It has to have velocity, right? So
Yeah.
max kinetic energy is going to be where max velocity is. So we can come down here at the bottom, the middle position. We can say max K is going to be at that middle position. Try to shrink my text box here so it doesn't cover everything up, which means if that's max K, up here at the sides where it stops moving, it's going to have minimum K. So the end positions, the far right and far left position, will be minimum kinetic energy. Oh, I made that a lowercase k. We can't abide that, so let's do that again. Minimum capital K, because I want to keep my variables consistent with what we would expect. All right, so that's kinetic energy. We know that there's a relationship between kinetic and potential energy. What happens when potential energy of an object drops? I have something that's at a high position and I let go of it and its potential energy drops. What is it gaining? If it's losing potential, chances are it's gaining kinetic. So if we have minimum kinetic up at the top position, oh, hey, guess what? We've got to have max U sub G, max potential, which means both sides will have max well, I'm going to leave that. And then that means when it's at its lowest point, it's going to have minimum UG. That makes sense too, right? It's losing K, or sorry, it's gaining K, it's losing potential. Then as it goes back up, it starts losing K, slowing down, and gaining potential as it moves higher and higher up. So the only thing left that we have to put on our diagram is where is the equilibrium position. Equilibrium position is where is the pendulum with no applied force. Where would you say that there is no force acting on the pendulum? No.
At the bottom?
At the bottom. At the bottom, where you have minimum acceleration, that is because you are at the equilibrium, or sometimes what we call the rest position. Why do we call it the rest position? Well, think about what happens to this pendulum. If I let this pendulum run for a while, what's it going to eventually do?
Stop at the bottom?
Stop at the bottom. It's going to come to rest. The rest position is where it stops. And this works for any simple harmonic oscillator. Okay, they go from maximum potential to maximum kinetic at the rest position to max potential again. And then if they slow down because of air resistance, because of any kind of friction, heating up of the string as it moves back and forth, they eventually will settle down to that EQ rest position. If I had my Newton's cradle, I could run through showing you how that looked, and you could get a nice visual of that, but we're not going to worry about that. All right, so that's it for our pre-lab stuff. Now, let's see if we can move on to doing the lab, and I'm gonna keep drinking my tea out of my Ironman cup.
I made tea and I drank all of it, and now I'm all sad.
I like chai tea. It helps keep me awake in the morning.
Chai tea is good. I got a box that's 6 different kinds of tea, and there's 6 of each.
Nice.
So,
all right, so this is uncharted territory time. You guys ready for lab at my house?
Yeah.
Okay.
All right, so this is a pendulum setup. And I'm going to be ducking in and out of the camera here because I'm going to have to work on this pendulum setup. Basically, what we've got is a bar sticking out next to a meter stick, and we're only missing one thing. We're missing the actual pendulum. So we need something that will be serviceable as a pendulum. And I told you a little while ago that you usually have a mass called a bob, and you have some kind of string or something that it can oscillate back and forth on. So we've got that, and I'm going to be able to tie this on here, and this is where I have to get a little creative because I have trouble seeing this close up. I don't have my glasses on. Look at that, perfect. So you can see that. I want to make sure that this stays in the screen, and when I swing it, you can still see what's going on. Maybe I will rotate this 90 degrees here when I get it set up, but this just gives me an idea of how high up it should go. All right, so I'm going to take a look at some of the lab stuff here in just a second, but I wanted to show you some of this equipment, and this is not to torment you because you don't get to play with this, but just to show you what we're going to be using, and I'll drape the extra string out of the way. So let's go back to our lab sheet and the materials, pendulum materials. It says washers. I've got some masses we can use. A meter stick, we got one built into that stand. A timer, oh goodness, I'm gonna have to use my phone. So hopefully you'll be able to see my phone at some points of this. And pendulum materials, well, that's all the other stuff. Procedure, investigate 3 factors using good experimental design. We don't want to use great experimental design. We don't have time for that. We're just going to use good experimental design. You're going to check the amplitude of oscillation, the pendulum length, and the mass of the pendulum bob. So 3 things that we're going to change while we are doing this lab. We're going to change the amplitude. Amplitude just means how far back you're starting your pendulum. Are you starting it where it's almost at rest position, or are you starting it back several inches, or starting it back all the way at 90 degrees out? Amplitude. Next, pendulum length. That's the length of the string of the pendulum. And then last is the mass of the pendulum bob. Any thoughts about which one of those things would cause the pendulum to do something different?
The amplitude for sure, because the further you pull it back, the longer it'll go.
Oh, okay. All right. So your hypothesis here is that if I take this pendulum and I let it go, or if I take this pendulum back here and let it go, then that's going to affect the time that it takes for it to come back and forth. Okay, make sense? All right, so that's what we're going to test. We're also going to check the mass. I have a way that we can change the mass that I've got hanging off of here. I've got a way that we can, well, I can just change the string and have it hang at different heights and see if that affects it. So we're going to check all three of those and collect some data. All right, I need some paper. It's difficult to do any experiment without having something to write on. So hopefully you've got some way of keeping track of your data as well. And we are going to look at amplitude, AMP. We're going to look at length, L, and we are going to look at mass, M. And let's go back to our lab sheet and make sure that we are doing this correctly. Measure the period of oscillation using 5 different amplitudes, 5 different lengths, 5 different masses. Graph the period versus independent variables. So the period is the length of time it takes for it to oscillate. The other variables are amplitude, length, and mass. All right, so we're measuring on our chart the period, capital T. If the relationship appears to be exponential or curved, you should square one of the variables in order to attempt a linear graph. See if we can figure out what the relationship is. Is there a linear or squared relationship? So step 1, is there any relationship between amplitude, pendulum length, and mass of the pendulum bob to the period of the pendulum? All right, so we're going to look at that. We're going to see if it's linear and see if we can come up with a mathematical representation of that for all 3 of those. What are some potential sources of error? That's the standard things to think about. Was your experimental procedure sound? Did you come up with some good reasoning on how to do this? Post-lab, draw a smooth, curved position versus time graph of the motion of the pendulum. So draw what you think the motion of the pendulum would look like there. So we'll deal with that later. All right, so first thing, amplitude. How do we measure amplitude? Okay, I'm gonna need a timer, clearly. And I'm gonna set it to stopwatch so I can stop and start it. Do I want to release this thing and time one back and forth motion? Does that seem a sound way to do this? Go 0.5 seconds. Thoughts? Any way to make my time measurements better?
Do multiple oscillations and take an average.
Smart. Okay, I like this. We're going to let it go back and forth 10 times. All right, so I'm going to measure 10 times back and forth, and then I'm going to get the average time that it takes for those 10 trials. That'll be my period. I'm doing amplitude first. How can I measure amplitude? If I had a protractor, which sadly I don't, I could measure the angle that I pulled it back, but I can measure the distance I pull it back. So it's roughly in rest position. And my goal for the first trial is going to be to upset it from rest position by about 10 centimeters. Okay? So my first trial is an amplitude of 10 centimeters. And then I'm going to measure 10 back and forth motions and figure out the period. Ready? Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, I got 15.4 seconds. Hey, I did 10 times. That'll make the math easy. So that means my period at 10 centimeters is 1.54 seconds. Now I'm going to do, let's try 20 centimeters. Let's try 30 centimeters. And I think I'm going to be lazy. I would have you in class do 5 trials. I'm just going to do 3 trials of each and see if we can get a relationship. So 10, let's do 20. 20 is about here. Super, super accurate. Can you tell how accurate this is? And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Huh. That's interesting. If you want to look at my timer here, let's see if I can quickly change this. I got 15.54 at 10 centimeters, and I got 15.45 at 20 centimeters. So what does that tell us? It's about 1.55 seconds. So I got 1.54 seconds and 1.55 seconds. What do you think? What does that mean?
There's either not a relationship or there's an error.
There doesn't seem.
Probably there's not a relationship
So
between amplitude.
if there's a relationship, it's super tiny, right? Let's try one more, because again, I would totally make you guys do 5 to be sure. Let's do not 20. Let's do 15. I'm going to split the difference. You want to do 15, or do you want to do 5? Or do you want to try to do 30? 30 is hard because it'll hit this stand. What do you think?
30 can be interesting to get a linear 10, 10, and 10 relationship to be able to calculate it.
Okay, I'm going to go for 30. Here we go. This is dangerous. Got to be very careful. Don't want to hurt myself. No, I'm not going to hurt myself. All right, ready? Here we go. This is about 30 centimeters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh-oh. Oh my goodness. Let's see if I can switch this out quickly. 15.63. So 1.56. So are we seeing a big increase there? Is that a significant increase that you would say changing the amplitude is changing how long it takes for this thing to go back and forth?
Not really.
Not really. And you know what's cool about this? If I was more accurate with my timing, sorry, I'm not perfect. I try, but I'm still only like 80% of the way there. What's cool about this is the reason we can use a pendulum and a grandfather clock, and you can have it sit there and go back and forth and slow down over time. It doesn't matter. The period of time will always be the same, no matter where you start the oscillation of the grandfather clock. So it doesn't matter if it slows down, it gets closer and closer towards the end. We could time this thing and let it go all the way till it was about to stop. It's still going to be about 1.54 seconds for each trial. Isn't that cool? I think it's cool. All right, next, length. Ready? For length, you know what I'm going to try? I'm going to try a length of the length that I have on here already. This is 60 centimeters. So length 1, 60 centimeters. And you know what? I'm going to average those 3 times together to get 1.55 seconds for my first trial for length. Cheating, but we already did one that has this length. Now I'm going to shorten this guy up and see if we can do this any better. Here's the trick of this lab setup, is when I tie this thing together, my knots become permanent knots, which we don't want. I try to tie these in slip knots so that they can, not the band slip knot if you're a fan, but tie these in slip knots so that it's easy to take this thing apart, and it's never easy. And these strings always come back to me when students do this with all kinds of knots in them that are unsalvageable. All right, so that was 60 centimeters. I'm gonna try, let's do 60, 40, 20. Does that sound reasonable? I hope so, because that's what I'm doing. 60, 40, 20. And this is going to be a ballpark because it's reasonably difficult to tie these perfectly. All right, get rid of our extra string. Oh, come on. Extra string out of the way. Don't need your. And we are about 40 centimeters. So second trial, 40 centimeters. Rotate this so that you can see it oscillate. And I will start it. Hey, do we care how far back I pull it back now? No, it's not going to make a difference. So I'm just going to pull it back. We don't even care how far I'm pulling it back. And I'm going to start this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 12.
Answer is -5.
I got, whoa, thank you, Watch, for trying to tell me my business. I got 12.33 seconds, which means my time was 1.23 seconds for 40 centimeters. Does that seem like we should stop? Look, we found it, right? That must be the answer. Should we stop? Heck no, we shouldn't stop. Always test multiple trials. So we did 60. That was our first trial was 60. That was 40. Now I'm going to try a pendulum length of about 20 centimeters. Can you guys hear one of my neighbors has chosen this time to do leaf blowing or something? It's a lovely noise. I don't ever have this problem at the school. All right, let's see how accurately I tied that off. Okay, that's more like 18 centimeters. That's cool. My next measurement is 18 centimeters. Reset. Don't care about my amplitude. And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see a difference? You can probably tell from how I was counting that time. 8.65. So that means at 18 centimeters, it was 0.865 seconds per oscillation. Have we concluded that there's something that affects the length of the time of a period of the oscillator? Yes? We feel confident? Good.
Yes.
Let's check one more thing. Mass. All right. I'm going to keep this small. I've already, let's see, how can we do this, make this easy? I'm going to do our last trial. I don't know what the mass was. I'm going to call it X, and then I'm going to add to that X a mass of 10 grams. So X plus 10 grams, and then I will do X plus 20 grams, and we will measure 3 periods for that. All right, so our first is just X, and we'll mass that out. We'll figure out what it was in a little bit. The mass of just the plumb bob, and it was 0.865 seconds. Next, we're going to do that plus 10. If this doesn't fall off, it will be awesome. If it falls off, forgive me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that time I got 8.41 seconds, so 0.841 seconds for plus 10 grams. Now I'm going to add a 20 gram mass to this and try again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I got 8.44 seconds, so 0.844 seconds. Does mass do anything to change the pendulum? I got 0.6,
No.
0.84, 0.84. Does it seem like mass does anything?
No.
No. All right, so mass is not changing the period of my pendulum. All right, so could you have done that with 5 trials, and would you have found anything different? No. You would have had the same answers. You might have gotten some more believable results, but we're going to call it good enough. All right, so now we need to measure the mass. So I'm going to go back to that, triple beam balance. And I'm going to do a little cheat because I don't want to have to sit here and untie that bob. I have an extra bob of the same mass. I'll put it on here, and it is, they're all pretty close. Since they're not exact, I'm going to call it 30 grams. So X was 30 grams, X plus 10 was 40 grams, X plus 20 was 50 grams. So I changed it by 10 grams each time, and I got the result. All right. That took a couple minutes longer than 30. We didn't start right on time either, but my goal was to get that done in the 30 minutes that you have to pay attention to me. And hopefully you guys got enough data there that you can answer the questions on the lab. So you should do 3 graphs. What is the impact of amplitude? You're going to be graphing amplitude 10, 20, 30 centimeters by a time axis of 1.5, 1. It doesn't change. It can be a flat line. Length, graph that. That would be easier to worry about the mathematical representation of it if we did more than 3 data points, but you can do a graph of that with 3 data points. And then mass, you can look at the mass and graph with 30, 40, 50 grams, and it was also the same time for each of those. So any questions about how that works? I think you guys got the idea by me kind of going through and giving you the results. Lastly, draw a smooth curve position versus time graph of the motion of the pendulum. So what does that mean? That means that when the pendulum is here, this is the axis of rotation, and it's here, it's doing this. It's going back and forth and back and forth. And you're doing position versus time. I want you to think about where its position is. You can call one extreme +1, you can call the other one -1, you can call rest position 0, and graph what it looks like it would be doing. And remember, it's slowing down as it hits the end, speeding up as it goes towards the middle, slowing down towards the end, speeding up towards the middle. All right, any questions for me?
How do you want us to turn this in?
That's a great question. How would you like to turn it in? Can you take a picture of it with a camera, have somebody help you do that, and either email it to me or, yeah, email it to me maybe?
Because I know you had said it was so good in the mind message. I didn't know how you wanted this to.
Yeah, you know, if you can get it to me through email, that would be perfect. Do your best representing the graph. I'm really, since we're only doing 3 trials for each, I'm less concerned about those first 3 graphs. I'm really more concerned with, can you come up with an accurate representation of position versus time for the movement of a pendulum in general? And I think if you start to think through it, it will look like something very familiar. You will probably see, oh, okay, I know what kind of graph that is. Once you start it, it'll pop to your head. Oh, okay, I get it. Good?
Yes.
Okay. It is a graph type that you have seen before in the past.
Cosine graph.
Oh, come on. You're just going to go right there and cheat and tell everybody. Yeah, yeah, it's going to look like a cosine graph, right? Well, it depends on, it could be a sine graph. It depends on where you start your graph, right? Are you starting it at 1 or are you starting it at 0 position? Usually with a pendulum, you start it at the 1 position. You could start it at the -1, but yeah. So it's going to be like a sine or cosine graph. So sketch something like that out, and if you can do that, and take a picture of whatever you got written up, and we'll call it a day. You guys feel like you did some good physics today? All right, cool.
Yes.
I'm going to pause the recording because that's all everybody needs.